Hello, Louisa. Good morning. Let's write some folks down. And Penelope and Ellie, good morning. Let me catch up here. And whoa, Feeny and Alicia and Bella. And now we're cruising. Amina and Sophie, good morning. And Chelsea. Good. Let's see if we got a couple more. We do. There's Antamine. And I'll wait another minute and then we'll start up. But that's 10 of us so far. That's pretty good. Today, by the way, we're going to take some questions from you, but first we're going to do a demo because that's why I came into school today and show you that. That will also wrap up chapter 2 and begin chapter 3. I got another one, so let's see who else is out there this morning. I'm going to go ahead and begin. I feel like I only got an hour. That's not that much. Oh, we got 2 more. So say hello if you're just joining me so I know who I've got. Can I prop this up a little more? Maybe I can. Maybe I can. Hold on. All right, hold on. Don't get seasick here. Try and prop this up a little bit more. Okay, that's pretty good. Okay, so when we ended last time, we were talking about the last unit, and I'm on page 141. The last unit that makes up chapter 2 in the book, and this is about entropy. Okay, entropy. So we got entropy is disorder. Okay, we got generally 2 desires or 2 trends in the universe, and that is maximum randomness and the other is minimum energy. The maximum randomness we call entropy, and the symbol is S, or we can say the change in S. Okay, we're going to use that again today. And the symbol for minimum energy, or energy in general, is enthalpy, which you had before, and it's the change in heat, okay, or heat of reaction. So it's sort of like who wins that. I'm going to give you an equation later today that will measure that battle. Who wins, okay? Disorder, minimum energy. Disorder, minimum energy. And it turns out, in terms of disorder, there's a last thing on page 141 that I want to talk to you about. Or is it? No, it's page 139. Okay, so for compounds, if they have more ways to join, then they have greater entropy. Have more entropy. In other words, let's compare NO and N2O4. Now, NO is obviously going to be like looking like that. N2O4, I don't honestly know. I'm going to guess it's the two N's and O's. But the deal is, this one, because it's bigger, has a lot different ways it can rotate and move around. She put that so nicely, Cheryl. So I just want to, frankly, copy her language because it was so nice. They have more possible rotations and vibrational orientations. Or just orientations. Okay, here's what I mean. Here's my NO molecule. There's not a lot it can do, okay? But once I got into O4, I don't know how I'm going to do this. I need like 8 pairs of hands. It can rotate and be oriented slightly differently, even with the chemicals still bonded together. So there's more possible rotations. So what I'm trying to say is N2O4 has greater entropy than NO. And you'll see those values in the book there. Okay, so page 139, all right? Okay, that having been said, I want to do something related to nitrogen as a demo now to kind of wrap up chapter 2, basically. So it's going back a little bit in time. Put that down a bit. Ooh, it's white back there. Good. Okay. I got 2 compounds here, and I'm going to show it to you. Actually, I'm going to show it to you first. Here, let's get ready here. Here's our demo. And I got NO2 and N2O4. The way I got these is kind of interesting. Both are formed when I put copper in a nitrate solution. It's like nitric acid or whatever. So I got nitrate plus acid, I got H plus, and I get Cu, I think 2 plus, it's like an oxidation. I get some NO2 and N2O4, both of those form. And I probably get some other stuff, maybe some water or something, I don't know. Anyway, it's not a full reaction, but that's how I got it. I add some copper metal and I throw it into nitric acid. Okay, just for grins. So here it is. You can't see it, so I'm going to now push this up, and I'll push it back down. Don't get all worried. So there it is. It's brown. I'll bring it closer to you. And I'm going to show you that I made 3 of them. I'll try not to stand in the way. And I tried to make all 3 about the same intensity of brown. That one's a little bit not the same, but I tried to make 3 all the same this morning. It tends to leak out over time, so that's why I had to come in and do it in school. So there they are, the combinations of these 2 gases. What I want to do is, and it doesn't take long, I'm going to keep one as a control, okay? And I'm going to take the other 2 and I'm going to put them in ice water and hot water. So in ice water, color, and in hot water. Okay, ready? I'm probably going to make a mess in here and get Miss Graff all upset with me. She seems to have taken this over. It's not working. Okay, so I got an idea. All right, more than one way to skin a rabbit. Oh, sorry about that. I'm going to put the ice water in over the top. Yeah, baby. Okay, that's going to work. All right, see that? So it's sitting in ice water. I'm going to put something on top to keep it there, other than my finger. So let's put this box of figs on here. Yeah, that's a good weight. So I'm going to put that on here and let that sit in the ice water, okay? And at the same time, I got to get some hot water. Stay. Okay, I got to get some hot water because I'm going to put some of the gas here in another flask and some hot water. So here we go. That's enough of my ice water. Let's get some hot water. I'll be right back. Don't go anywhere. Okay, it's not the hottest hot water, but it's going to have to do. So I'm going to put another one at random in here and hold it in there. And I'm going to make the whiteboard appear behind me here so you can see. Already, let's compare. God, that's got a leak. I can smell it. Shoot. Come on, stay in there. Stay in there. I don't know if you can see any color difference or not. Can you tell any difference? Which one looks darker? Can you tell from there? This is the hot water. This is just the control. If you can see that difference, let me know and I can see how close. Which one's looking darker in color? Hot water or the control? You can see it. The one with the hot water looks darker. Okay, all right. Okay, so that's what I wanted to ask. Okay, then I'm going to now compare the one in the cold water to the hot water. Hope that's even more clear. There's cold water, there's hot water. Is it even more clear now? I hope this one's a little more see-through. Tell you what we can do. Let's just do the control. That would be smarter. So here's the cold, here's the ice water, and there's the control. And I'm like standing in the way, so not there you can see. Okay, all right. So that's the cold water, that's the ice water control. Ice water control. Which one looks darker now? Ice water or the control? Just waiting for your response. Can you see any difference? Ice water control. May not be much different, but I hope you see it. The control, good. Okay, yeah, so the control should be a little darker. All right, let's just hold up the ice water and the hot water again. I can do it without making a mess here. So there's, oh, that's pretty clear even for me. So there's the hot water, a bit darker than the cold water. Okay, we're going to see why that is right now. Okay, oh, I got ice everywhere. Shit. Okay. This graph will kill me, but she won't know it's me. Don't tell her. It's actually a science room anyway. Don't get me started. Okay, so I got Lola. Anybody else just arriving? All right, so yeah, let's write some stuff. So here we go. So I've got this going on. I've got NO2. Oh, hello?
Oh, hi.
Sorry, I took your room because I need one.
Okay.
I'm doing a demo and a live stream.
Okay.
Thank you.
Oh,
I'll put everything back the way it was.
Chris, I'm not even worried about it.
Good.
I was just gonna come and, do some coffee and
Okay.
get my, are you in class right now?
Yes.
Oh, sorry, hello, sorry for interrupting.
Okay, so here we go. What's happening, folks, is these two chemicals are going back and forth in equilibrium, okay? So I got N2O4, but this is not balanced. Help me balance it. So check it out. I got NO2 and N2O4. I can balance it by doing what? How can I balance that sucker? And then we'll continue with what's going on. Thank you, Amina. Thank you, Penelope and others. So you're right. I need two there. So now check this out. I got to tell you, one of these gases is clear. One of them is brown. So we can figure out which one by using our logic. Okay, I had more brown color at a higher temperature. Which side would be more favored at a higher temperature? Which chemical? Or you can say reactants or products. Which chemical would be more favored at a higher temperature? Hint, they're both gases. And I'm increasing the temperature when I put them in okay, well, I make them hotter, of course, when I put them in the warm water bath. So which side is favored by a hotter temperature? Or I could ask you, which side would you add? Product side, product side. Okay, I'm getting some guesses. Let me ask you this. Which side would I put heat into to get the other side? Which side would I add heat into to get the other side? So use your logic. Which side would I have to add heat to? No. See that guy? That's big. What do I got to do with it to get two of them out of here? I got to take this guy and do what with it? What do I got to do with the N2O4 to get two of these guys? Huh? Yeah, Amina, right. Because why? What do I got to do with this guy? That's that. Now there's two of these. I got to take it and this is really the crucial thing. Here's N2O4. What do I got to do with it? All right. Thank you, Mina. I got to break bonds, Chelsea. I got to break it apart. So what that means is I got to put the heat here. Now remember what we talked about with Le Chatelier's principle. So if I increase the temperature, it's like adding in more heat. Okay? So if it's hotter, I'm adding in more heat. Now, everybody, it's going to shift this sucker towards reactants or products if I add more heat. It will shift it towards reactants or products if I add heat, which I did in the hot water. Which way will it shift it? So I'll say more if hotter temp. Reactants, yeah, everybody, Lola, Alicia, Mina, Penelope, good. So more reactants. So therefore, which gas is probably the brown one and which one is clear? So which gas is the brown one? Which one is clear? And I'll label them over the top of each. So which gas is hot as brown? Exactly. So that means which side is the brown one? Which side is clear? Ice is clear. No, 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 Bella. I don't care about the ice. I care about the gas in here. So which chemical, N2O4 or NO2, which is brown, which is clear of the two gases? Which is brown, which is clear? The hot one is NO2, right? I don't need the 2 there, ladies, but NO2. The cold one is this, right? Okay, so this one is, so the hot one, in other words, the brown one is this one. At hot, I get more brown color. So that's brown in color, and this is clear. Hey, that's cool, isn't it? What's even more cool, by the way, I took them out now, and now look at it. They're all kind of the same color now. Okay, I took them out. It takes gases about a minute to reach equilibrium, and then they're like back to the way they were. Okay, because I just made them a few minutes ago in the lab. All right, some more reactants have out of temperature, and browner color when hot. So NO2 is favored at, just so I know you're following, can you all fill in the blank? So NO2 is favored at what? So NO2 is favored at what? Just so I know you're following. So NO2 is favored at, and then you can add here. N2O4 favored at, yeah, higher temp. Thank you, Lola. Thank you, Anthony. Good. So NO2 is favored at higher temps. That's the brown color. And N2O4 favored at low temps. Now, I got to tell you guys about this gas. There's a reason I got it on a stopper. Well, I don't want it to escape, but I don't want to breathe it. NO2 is a favorite gas that you've seen in the summertime in Berlin, or most states if you've been in pardon me, you've seen this in the summertime in Berlin, or a lot of the year in places like Beijing and Shanghai, okay, or Egypt. This is a main ingredient in what? NO2, probably both of them, but certainly NO2 is found in this lovely gas. Can you guess where you found it? If you've been unlucky, you've breathed a lot of it. I don't like to breathe it. Where have you found this gas? Anybody guess before I write it up here? It's in air pollution, folks. Another name for air pollution? Smog. Okay? You know that brown stuff you call smog? Guess why it's brown? Because it's got this in it. Wild, huh? Okay, so isn't that kind of cool? So that's why I came into school today, to show you smog, okay? With Corona, the skies are a lot clearer in Berlin anyway, even last summer. But and in Beijing, they had some amazing days where they could actually see something instead of lots and lots of this, okay? So air pollution, NO2 is dinade. Okay, it's not everything, but it's one of the things in air pollution, okay? And it does provide most of the brown color. Questions from you? Am I still on? I am. Let's see if you got anything you want to ask about with that wild and crazy. I hope it was a gas for you too. The world's full of bad jokes. At least AP Chem is. All right. Any questions? We all right? Okay. Good. Now, back up here, I'm going to erase this in a second. If you missed some of that, just look at the video later. Do you have questions on chapter 2? So this is your time. Okay? Chapter 2, any you want to ask about? So chapter 2 problems, you can see that. God, I'm not used to chalk dust anymore, am I? Okay, I got my book here. Let's see for a few minutes if there's any you want to ask about. Give me a page. Yes, and I got one already from Alicia. Here she goes. 180, I'm getting there, everybody. 180. Thank you, Louisa. 180, 24D. Let's look at 24D. Okay, so we got this. Oh man, this is going to be hard, Alicia, because I really almost have to do the whole frickin' problem. I can't really do D unless I get your answers for the whole thing. Let's see. PCl5 decomposes into PCl3 and Cl2. A pure sample of phosphorus pentachloride is packed into an evacuated 1 liter glass bulb. The temperature remains constant while the pure sample decomposes as shown. Okay. Explain why the pressure increases and as, okay. All right. Okay. First thing we need to do for anybody is write a reaction here. So we got what? PCl5 in equilibrium with PCl3 and Cl2, probably. Is that right? Yeah. Well, they're all gases. So let's read A together, okay? Why does the pressure increase in the container as the reaction goes to equilibrium? Initially, you only had this one. I don't think I need an ice table to explain this. Can somebody explain it? Why does the pressure go up as the sucker reaches equilibrium? What happens? What happens to some of this? And compare the number of moles of gas on each side. So who can answer A? If you have already, tell me what you wrote. 24A. So why did the pressure increase in the container as it reaches equilibrium? What's going to happen? I got all this stuff. It's going to do what? And that will do what? I know it's relatively early, but gets used up. Yes, good. Keep going, Bella. It gets used up. Well, at least a little bit of it. Probably not all of it, but it's going to make some of these. What's going to happen when it makes some of those? What's going to happen when it makes some product? Hint, they're all gases. What does that mean? I'm going from what? Volume increases? No, the volume can't increase because it's in a flask, Amina, so the volume cannot change. So instead, the pressure increases. Why, Amina? I'm going from what? 1 to 2 moles of gas. So even if one molecule only breaks up, it's going to make more pressure. Why? Because I'm making more moles of gas. Alicia has it. So the pressure increases, not Anthony, higher pressure. But you got to say why, because there's more moles of gas. Okay? So make sure you can see that. There you go, Amina. So double the number of moles you're making, and by golly, that's what's got to happen. Do you miss those bells? I do sometimes. That's it. Let's go to B. Determine the partial pressure of each when it reaches equilibrium. Calculate Kp for the equilibrium. All right, so I'm just going to get, okay? That's my hit for B. Do an ice table, and I think you'll get B. And then calculate Kp for the system. No, you can't do that for B. No, I'm sorry. Nah. Why? Because you don't have the You don't have the thing yet. Okay, I'm going to ask, okay, give me a little help, somebody. What'd you do for B? What's a way I can do B for this sucker? What's a way I can do B for this sucker? And I'm going to ask also Alicia, because I'm guessing you got B, but let's see if somebody else can jump in here. What's the tool you use to get B for page 180, 24, 24? I know how I want to do it, but I want to see if you can figure it out, because whether I can do it or not doesn't really matter much. You guys have to do it. Let's say you used an ice table. All right. I guess that's what we got to do. All right. Okay, so here we go. So we got PCl5, PCl3, Cl2. I wasn't going to do it, but I'm just going to do it now because I'm just going to 1, 0, 0. Why do I know I've got zeros here, gang? Why do I have zeros there? Why do I know I got zeros there? Thank you, Alicia. Super. Good. All right, so these are zeros. Everybody should be able to answer that. So I want you typing in. Otherwise, I feel like I'm all alone here at JFKS. So why are those zeros? Hint, look at the initial circle. Yeah, they form later. Thank you, Amina. Good. So initially, I've got only PCl5. It says that P total initially is 1 atmosphere. That's all I got, 1 atmosphere. Minus some amount X. Okay, look at it. It's 1 to 1 to 1. So if I got minus X, I got to go plus X, and suddenly I got, oh, but we know what X is. Well, let's see. Sorry. Okay, so 1 minus X, we got X, we got X. And I got the total pressure is 140. So I can't do products over reactants. Why? Because I don't have the P. Sorry, the P. The KP. They didn't give me the K. You're going to figure that out in C. But what I can do is what? I can say that if I look at equilibrium, if I add up all these, see what I'm saying? I get the pressure of Cl5 plus the pressure of pressure of, God, PCl5, the pressure of PCl3, and the pressure of P of Cl2. I'm sorry there's so many P's coming around. It's just P is pressure. The pressure of the main stuff equals the pressure of that plus that. So add it all up. Well, you know what that is. They tell you. It's 1.40 atmosphere, right? Atmospheres. It's in the second circle. And what do I got here? Look at that. A 1 minus X plus X plus X. Can the algebra get any easier? I don't think so. So I got, do that math for me. I got minus 1, so I got 0.40 atmospheres I got X minus X. I got X. Okay, so go back and answer the question, right? The partial pressure of each gas. Well, that's the pressure of which one? And then look at the other ones. I got these two are both X. So that's the pressure of two of them. It's the pressure of who and the pressure of who. Then the other one is 1 minus X. So I got to go 1 minus 0.40 atmospheres. So 0.6 atmospheres equals P of what? Let's see if you guys answered yet. No. You guys got to catch up, unless your internet's really slow and I'm just not seeing you. Okay, the 0.4 atmospheres, that's the pressure of which ones then? Go back and look at your ice table. Where's X? What is X? X is the pressure of what and what up here? Thank you. Okay, I got one person out there. So P, Cl2 and P, PCl3, because those are equal, right? Those are equal. Okay, and the other one is PCl, oh God, yeah, PCl5. So the 0.6 is that, and that's what I think Alicia got as well. I'll go back and check. Yes, that's what she got as well. So 0.6 and 0.60 and 0.40. Now we can actually get to, C is then easy. You guys can do C. Let's go to the one Alicia is interested in, D. Yeah? I'll put a little board space down here. All right, I got to take the sweater off. I'm dying in here. So, if the decomposition were to go to completion, what would be the total pressure in the system? Well, let's find out. Okay, so, D. For D, we need the Kp expression. So, Kp equals what? Pressure of PCl3 times the pressure of Cl2 divided by the pressure of PCl5. So, just so I don't lose anybody, it's products divided by reactants again, right? Because what? I got products divided by reactant, okay? You guys should do that so you can see that. Okay, there's my equation. Okay, the Kp then you got essentially, what's the Kp? From the last one. Geez, I got to do the whole frickin' problem. Okay, Alicia, what'd you get for the Kp? Just type it in and let's just put the number here. Because I don't want to do C. I want everybody to do C on their own because they need the practice. So Kp is what number? And then we'll figure out what's going on. Thank you very much. So 0.27. Good. Remember, there's no label, so it's just a value. Equals. Okay. She gets how to do it now. Okay. Then how do you do it? So D, what would you do to get the total pressure if the reaction were to go to completion? Actually, I don't even think I need that for D. Hint, everybody, I got 1 atmosphere here of PCl5. If it goes to completion, then I've got how many atmospheres of each one. So if one of that completely goes to one of this and one of this, then what's my pressure, gang? So I get 1 atmosphere of Cl2 and 1 atmosphere of PCl3. And if that's the case, if I got 1 atmosphere of each, what's the total pressure? Hint, 1 plus 1 is. So I don't need this at all. I don't need this at all. I just need to think about it. How do I know it's 1 and 1? Thank you, Amina. Because all of it is going to completion. So all of it, the 1 atmosphere, is changing over to the other 2 chemicals. All of this is disappearing and making them one of this, 1 atmosphere of this, and 1 atmosphere of this. 1 plus 1 is 2 atmospheres. Or however many sig figs you got. Okay? Good. I'm going to call it quits there and continue on with talking about chapter 3. Over break, I will be home. Feel free to write me either email or through the AP chat if you have questions on problems. Okay? I know I'm not telling you to work your whole vacation. On the other hand, if you're like me, you do have some time. Okay, so if you have questions, feel free to ask me over the break. I will be in Berlin, big surprise. Okay? All right, so let's continue on with the ideas of chapter 3, which is about thermodynamics. If I could find my sponge, what do I do with it? There I did with it. Okay, so chapter 3, thermodynamics, but I'm going to say it's also about spontaneity. Spontaneity. Or as they say on the AP test, is it thermodynamic? I have no idea what you're talking about, Anne-Sophie. Maybe you got an email I don't know anything about. I assume our chat will be where it is, but let me worry about that. Okay, spontaneity. So it's also called thermodynamically favorable. Usually they're talking about to go to the products. Or as I like to say, hey, is it third fab? Don't say that on the AP test, but I think of it as being third fab. Does it make products or not? Okay, so to be spontaneous or thermodynamically favorable, a reaction occurs by itself without any help or changes from outside. From outside, period. In other words, it's thermodynamically favorable if it goes, if it just does its thing. Like if I have something here and I put some water on some metal, some iron, it'll probably rust, and it would be thermodynamically favorable. Now, thirfab or thermodynamically favorable or spontaneous does not tell you how slow or fast. Can you still see that? Yes. reaction is. In other words, it's not about rate here, folks. It's about will it happen or not. Thermodynamically favorable means it'll happen. It'll make products. Like rust happening at room temperature. It doesn't tell you how fast. Like rust is thermodynamically favorable, but it's slow, okay? If I have a firecracker and I light it, it's going to continue to light and stay and burn, and it's going to be thermodynamically favorable. You betcha. We're not talking about the activation energy. Okay, let's assume that's already there. But then will the reaction keep going? Once I light a firecracker, it goes, and it's very thermodynamically favorable, and it's very fast. What about boiling water? It's not a reaction, but if I turn the heat off, once I get the thing boiling, it'll stop. It's not thermodynamically favorable at room temperature. Of course not. I need 100 degrees, right? But that's the idea. That's the idea. Okay, so I never have enough time with you guys. Let's review some stuff we had from previous chapters. Delta H. Okay? Heat of reaction. Also called entropy. Also called whatever. There's lots of names for this. Okay, turns out many thermodynamically favorable thermofab processes are exothermic. Energy is leaving the system. Example, a bonfire. Right? Lagerfeuer, bonfire. So I got something burning, and it's made of wood, and it's going to keep going. It's thermodynamically favorable. And energy is leaving the system, obviously. Okay, so almost all exothermic reactions are thermofab at 25 degrees C and 1 atmosphere, so standard conditions. Example, and here's the one I gave before. If I got 2 iron solid plus 3 halves of an O2 gas plus 3 waters, I get 2 FeOH3 solid. And that's the reaction for making rust. Rust never sleeps. Gotta love it. Okay, the delta H for this sucker is negative 780, holy moly, 0.6 kilojoules as written. I'm not going to say per mole because I got 2 moles of iron here. That's a lot. I know it's really slow, but it's very exothermic when it happens. Well, how come I can't feel the heat coming off of something rusting? Because it's too slow. The heat dissipates, okay? The heat leaves before your hand ever feels it, okay? All right, so however, ice melts at room temp, and this is endothermic So if I had a snowball in my hand when we had snow, of course it's going to melt in the classroom because it's above its melting point. But it's still an endothermic reaction, and it would be therfav, favorable at room temperature. So sometimes if I increase the temperature enough, I can make an endothermic reaction therfav. That's my point. I know you're still ready. You're still ready. We got to get some board space though. So raising the temperature, raising T can make an endothermic reaction therfav. And we're going to find out how to do that mathematically later on. But in general, systems move in the direction of minimum energy. In other words, often it's exothermic, so a negative delta H, exothermic. Okay? So that's sort of the scoop, okay? Generally things follow exothermic reactions, no problem. Okay. Some of this I think we said, so let's see if we did. To get entropy, the disorder, S, we just do what? The change in S equals the S of the final minus S initial. Or another way to say it is delta S equals S of the products minus S of the reactants. And I think we had that already because I remember making the bad joke about Sprott and Sriak. Increasing the temp of a substance increases its entropy. Makes sense, right? If I got particles, the more those particles move, the more disorder. Okay, so higher temperature, more entropy, more disorder. And a couple things to know. A reaction with more moles on the product side is increasing in entropy. kind of like the one we just did with all of you, where it was the PCl5 going to PCl3 plus CO2. I went from 1 mole to 2 moles, so it had an increase in entropy, this reaction, right? It went from 1 to 2 moles, so more entropy, more disorder. Okay, we're not going to do that. Last thing is crystalline solids. Example, NaCl salt, right? Solid. Have entropy equal to 0 at 0 Kelvin. Whoa, but that kind of makes sense. So if I got it that cold, 0 degrees Kelvin, it's not moving. Therefore, there's no entropy, no disorder at 0 Kelvin. Everything's nice and ordered because it's flipping freezing cold there, right? This might be reviewed too, but let's just find out. The second law of thermodynamics by the way, the first law, you know, it's the law of conservation of energy, right? Energy is neither created or destroyed, but it can be transformed from one form to another. That's the first law, but that we don't care about that. The second law is that entropy is always increasing in the universe. Example, smoke. Think of smoke. It's just dissipating, and the more it dissipates, the more disorder. If I make smoke, it's got a lot of disorder. So it's increasing even if entropy decreases within a reaction, which is known as the system. So I can make something more organized, but it costs me a lot of energy and I end up giving off heat to do it. For example, I clean up my room. Okay, it's nice and orderly, but I gave off a lot of heat, a lot of energy to do that. So overall, even though the room is clean, I've given off more heat to the universe. So entropy has increased. Entropy in the form of heat. Heat's the most common form of entropy. Okay? Good. Let's get to the heart of what I want to talk about. Free energy. No, it's not a yard sale from America. Free energy means this thing, delta G. Is a measure of thermodynamic favorability. Oh, what a terrible word. Favorability? Okay. Or we can just call it, it's a measure of spontaneity. If delta G is negative, so it's less than 0, the reaction is perfect. And if delta G is greater than 0, the reaction is not perfect. Okay, so you're probably wondering what the heck this delta G thing is. So that's where I got to let you catch up. And then I've got to tell you what that is. Delta G is a beautiful thing. It's telling you who wins, minimum energy or maximum randomness. So delta G is weighing these two and says, you're the winner or you're the winner. And it does it with a beautiful reaction, which we're all going to put under our pillow and memorize, but you will because you'll use it so often. It's super useful. Essentially, it's a tale of two desires. You've read A Tale of Two Cities by Chuck Dickens? I hope so. Good book. This is A Tale of Two Desires. On one side, I've got delta H. That represents the minimum energy. I'll call it a tendency instead of a desire. Okay, tendency is a lot less romantic, but there you go. And I'm going to subtract the delta S, and let's leave a little space here. And that's, of course, the minimum energy. Or that's the maximum randomness. Randomness tendency. Okay, so it's this battle. Minimum energy, randomness. Which wins? Well, randomness, it increases if I have temperature higher. So I'm going to put T in here. So T in Kelvin times the change in entropy, that is the randomness. Well, I'm going to take that away from here. The winner of these is delta G. And we're going to make them all 0, 0, 0, 0. I know I've run over 3 minutes. Thank you for your patience. 0 means standard conditions. We'll use delta G when we start after break, but that's at least enough for you guys to start chapter 3 if you're so inclined, okay? We'll talk about using it, but that's more or less the guts of 3.1 and 3.2. And not 3.3. So we've done up through 3.1 and 3.2. So if you want to do at least that far, that'd be peachy. Sorry, I took an extra 4 minutes. I try not to do that, but that's life. Okay, be well, everybody. If you missed some of this, I'll post the video right now, and we'll see you in February. Okay, email me if you need help on something in the meantime. Bye.